how do we continue to support the growth, prosperity, but not really affecting the environment? And that's a challenge. I mean, like this, I don't have the answer to that, right? Like, and I think if we had the answer to that, then we wouldn't be where we are, and we wouldn't be having these type of discussions today. But what I know is that the answer to that really has to pass through decarbonization. We need to stop emitting, because if we continue to emit, we're going to continue to see these changes, and perhaps more aggressively as years go by. And we need to get to zero, and probably even to negative, because we have historical emissions, as we were discussing before. We have already put out a lot of carbon into the environment that we're going to probably have to bring down and recycle, or actually sequester, because there is no way to recycle. We have much more than what we could use out there. And, you know, there's a lot of people trying to do this. And there's a lot of things that need to be involved. They involve policy, they involve economic models, they involve people buying into it, but they also involve technology. And that's where engineers are uniquely positioned to really make an impact. And then the question is, okay, so what is it that is needed? To answer that question, you need to understand where emissions come from. And this is part of the discussion that we're having right before I started speaking. Emissions come from basically everything that we do. And this is sort of a division of sectors. You can divide this into many different ways, and you have seen similar pictures. This is in the US. In the world, it looks a little bit different. Like manufacturing is a little bit bigger, transportation is a little bit smaller, because we just like to move a lot in the US. And this is a lot long. What is nice is that we have technologies to decarbonize many of these different sectors. Like we're seeing the deployment of solar, wind very broadly. There's plenty of wind energy being installed for New York, and that will continue to increase. We have batteries, like cars are being electrified, which is fantastic. Of course, that comes with some problems that we need to mitigate with, but that will help us decarbonize transportation to a very large extent. We can probably grow fertilizers, have fertilizers in a cleaner way, because we have clean hydrogen. We can produce hydrogen from water, and then that can help us produce ammonia. But the things that worry me the most are the things that we don't have, right? There are sectors of our economy that rely on technologies that we don't currently have the ability to fully decarbonize. And these have to do with things like having enough long-term energy storage so that you can store energy in the summer and then use it in the winter when you need it, rather than on a daily basis. People still like to eat cows, including myself, and cows emit methane, and we haven't really solved that problem. And I think people will continue to like to eat cows, so we're going to have to solve that problem to some extent. Hopefully, we can stop eating a lot of it, but that won't change that significantly. We're humans; we like to be connected, so we're going to continue to fly and like be with the people that we love and care. And I don't really see us in the next century decarbonizing aviation, but you can maybe bring circularity to aviation, and that will probably mitigate that problem. And then the big one is industry. We don't know how to make steel, plastics, or cement without emitting CO2. And when I say plastics, really, that means making chemicals that we then bind together to make materials like plastics. So my group and the effort that we started to do at NYU, called the Sustainable Engineering Initiative, is aimed at tackling some of these problems and figuring out those engineering foundations that can help us develop these solutions. And we frame this in a framework which is called ANRAD, which basically figuring out those solutions that will help us avoid, mitigate, or remediate climate change and environmental pollution. And then we know that the climate is changing, so we're going to have to adapt. So we're also going to have to use our engineering skills to help us adapt to the changes that are coming. And it's based on 3 pillars. And I think probably education is the most important one of them, because I love what I do in my research, and I think we're doing some cool stuff, and I hope that our research will have an impact. But ultimately, it's students that are going to go into the world and really change it and change industry in a way that hopefully moves towards decarbonization. There's plenty of research going on, and we're trying to grow the research on these sectors. But then research does nothing unless it leaves the lab. So we're really trying to enable an innovation ecosystem that can take these solutions and maybe even policy ideas and put them out into the world so that they can actually have an impact. Then we can move on and start to develop these Android solutions that we need. In my group, we work in a lot of the areas where we don't have solutions. And I think the biggest part of the group really focuses on things that are related to decarbonization of industry, manufacturing technologies. When you think about manufacturing technologies, there's three big things, as I mentioned before: cement, steel, chemicals, plastics. They roughly account 30% each. The chemical industry as a chemical engineering is like where I spend most of my time in, and hopefully we can get into steel and cement at some point too. This industry emits 30% of the industrial emissions. And then the question is, where does this emission come from? For those of you that are not chemists or chemical engineering, what you should realize is that we built a chemical industry next to refineries. So the chemical industry exists because of oil. So we discovered oil. We wanted to figure out how to make fuels out of oil. We refine and distill it. We figure out that, oh, there's molecules there that we can make stuff with. And then we build a petrochemical plant next to it to make chemicals. And that petrochemical plant makes chemicals that like then go to 96% of the things that we make. There's more than 70,000 products. And because of that deep interconnection between the oil industry and the chemical industry, all of the energy, or the great majority of the energy that goes into chemical manufacturing, more than 93% of the process, require heat from fossil fuel combustion. Like we just had, natural, well, now we have natural gas. Before it was oil and coal that we just used to generate that heat and carry out the chemical transformations that make all of these materials. And what we have been trying to do is think of a different paradigm where perhaps instead of using fossil fuel to generate heat to drive our chemical reactors or separation processes, I don't know if you have driven through a petrochemical plant and seen like one of these big distilling towers. Like these are distillation towers, right? Like these things are humongous. And you also have these really big towers to make ethylene and propylene, like these are ethylene crackers. So each of these things costs like $1 billion. So I mean, like there's a good discussion to be had on how to transform that like in the long term. But all of these units require heat. And there's multiple ways that you can eliminate CO2 from that energy. A simple one is, well, why don't we just electrify that heating, right? And companies are trying to move in that direction. That's a high technology readiness level. So for those of you that haven't heard about TRL, so this is the way that we measure technology development, and usually you want to have. Oh,
I think that's me. Yes.
What did you ask me to?
Start the video. Sorry. Correct.
Okay. Let me.
There you go.
There you go. So these technologies, they're not ready, but people are working on them, right? You can use, ohmic heating. You can use heat pumps. There's multiple ways that you can deliver heat to chemical processes. But there are other ways that you can also think about this. An intermediate way is using hydrogen. So I'm sure you have read about hydrogen. Like hydrogen is in the news. It's all over the Inflation Reduction Act, which is really the Climate Act. Although climate is a dirty word in America, so we call it inflation reduction for some reason. The idea here is that we split water, we produce oxygen and hydrogen, and since we have these plants already running on heat, why don't we just burn the hydrogen instead of burning natural gas? You're gonna have to retrofit it, because it's not the same, like it doesn't have the same heat capacity, like there's some safety implications from doing that. But you might be able to do that, and the industry is thinking in this direction. So there's a lot of efforts to build electrolyzers. There's hydrogen, not only for the chemical industry, but also for other associated manufacturing industries. Then there's two things that you could do to bring electrons closer together to molecules, and perhaps doing chemical transformations more efficiently, so that you don't necessarily waste energy by going from different forms of energy, from electricity to heat to chemicals, so that you can bring electricity using electrochemistry. So that's Well, branch of chemistry that where you can really have literally a cable and you put it together with a chemical mixture, and then chemistry happens, like chemical reactions happen. And if you control that, then you can make the molecules that you need. Another way to do this, which is plasmas. So plasmas are ionized gases. They're really high energy, so they can do really interesting chemistry that is difficult to achieve otherwise. So these are areas that my group works on, pretty much all of them, maybe with the exception of the first one where we only think about it, but we don't really work on it. But like one of the big challenges is always to think about where to start. I told you, we make 70,000 products in the industry. And each of them have a carbon footprint associated with it. This is an idea on like what happens in a petrochemical plant. We take our oil and gas, we make our fuels, and then we make some chemical feedstocks, which are the big boxes here, ethylene, propylene, butadiene, so those are called olefins. And then these are aromatics, benzene, toluene, and xylene. And then we functionalize them, and then we put them together in layers to make chemicals. And that's what makes your clothes that you're wearing, that's what makes the shirt, that's what makes the carpet, that's what makes the paint, that's what makes the car, that makes everything, right? Except the cement and steel that are holding the building together. And this is a hard question because each of these little arrows that you see here is a different chemical reactor, it's a different separation column. They all have their special issues associated with them. So one way to think about this is that, well, we can start with the big ones because they're the large volume, they have the largest carbon footprint. But the challenge there is that they have been so optimized that the cost of these materials is very, very low. So 1 kilo of ethylene costs $0.8. So less than $1. So being able to develop something that can compete with state-of-the-art technologies there is really hard. So what we decided to do was start on the right, because 1 kilo of decarbonization costs $3.5 to $4, much higher. So it's still a commodity chemical, it's still a large volume, but it's not ethylene. So the reason we decided to work with that model of decarbonization, which for many of you don't mean anything, is because it's a precursor to nylon 6,6, which probably you have heard about. So nylon is in your jacket, your winter jackets. Probably there is nylon all around the carpets. Your cars, plastic cars in your cars, they're nylon too. So it's a really great performance material. And the reason we started looking into this molecule, well, first of all, is because we got money. That's usually how it works. We got money from the H&M Foundation to develop sustainable paths to nylon manufacturing. And then the scientific reason for it really is that there is already an electrochemical way to make this molecule that has been practiced in industry since the 60s. And it's used to produce more than 500,000 tons per year. This is the only large-scale petrochemical process that uses electrochemistry. There are some other electrochemical processes in aluminum manufacturing, in chlorine manufacturing, but for petrochemical, this is the only thing that operates this scale. And when we started looking into it, there were about 10 papers on this. So, and a lot of open questions, and we still have a lot of questions. And now, we impose 6, 7 papers on different aspects of these things. And what we really wanted to do was to understand what makes this reaction so special, so that we can use electrochemistry to manufacture these and learn from that, and hopefully percolate through that network that I showed you before. Yes.
And by electrochemistry, you mean using electricity
instead
of fuels, right?
Instead of heat, yeah. Instead of fuels, yeah. So the first question is always, how does this work, right? And I don't mean to go through all of the chemical details of this process, but just to give you a sense of what an electrochemical reaction looks like. So you have 2 parallel plates. So these are electrodes. We send electricity through that. We feed in our reactants from one end. We get our products from the other end. Usually we build flow systems of chemical engineers because we want to produce continuously at large scales. And then at the surface of these electrodes, reactions happen. So you apply a current and electrons jump from the metal to the chemical molecules. And then as they jump to those chemical molecules, they produce what you want, but they also produce a lot of other things that you don't want. And as chemical engineers, a lot of things that we do is trying to figure out how to design and operate these reactors. So we get high throughput, produce a lot, and high energy conversion efficiency, unfortunately. So as I said, I don't want to necessarily like dwell too much on the details, but like I wanted to get one thing. There's this reactant, which we're going to call AN. We're going to make this product, a nitro of ADN. And the main byproduct is this one here, PN. And you can sort of see like the trend. So this molecule requires 2 of these to be created. So that's a dimer. That's what we call a dimer. It's 2 molecules. This is the same molecule, but without that double line there, that double bond. So that just, you add 2 hydrogens into it, and then you get this molecule. So this requires only 1 equivalent of the reactant. This requires 2 equivalents of the reactant. And the key here is that you want to maintain a high concentration of the reactant close to that plate electrode, so that you can then transform more towards the product that you want and avoid the production of the byproduct. Okay? And we did a lot of things. We figured out like what electrodes we had to use. We figured out what pH range we had to use. We added some chemical magic inside, and like Daniela, my first PhD student, sort of like reverse engineer a bunch of patterns and whatnot to figure out how to operate this at really high selectivity towards the molecule that we want. And that had to do with all of the things that I told you before. Like, how do we formulate the electrolyte that goes inside of that reactor and goes together with the reactants and whatnot. And one of the things that we realized was we could achieve high selectivity, which we measure usually by something that we call paradigm efficiency. It's not really important. That just means like how much are you making of what you want versus what you don't want. We do this at a given current density. And in electrochemistry, we measure currents, but as you measure currents, that's the same thing as a reaction rate or production rate of what you want, because you have that deep interconnection between currents and chemistry. But as you increase the current or the production rate, the activity goes down. And the reason for that is because you consume the reactants that you have next to your electrode, and you start to make your main byproduct. So we started to think about how do we started to think about what was happening here. And we realized that we were probably observing something that we call mass transfer limitations. So what is mass transfer? It's movement of mass. What is the mass that I care about here is the reactant. So I just wanted to make sure that I could move the reactant fast enough to the surface of that electrode so that I had enough there to make the product that I want. So to do that, I had to better balance the way that I deliver the current and I allow the molecules to move towards that surface. And we started to think about pulses. So instead of having a constant current, why don't I apply a pulse so that the reaction starts to take place? But then as I deplete my reactant, I stop the pulse. And I allow the reactants to go back to that interface. So in that way, I can maintain a more or less constant concentration at a higher level next to my electrodes. And we can model these things, like perhaps not as well as like many of the computer scientists model their own systems, but we get a sense of what are the right time scales of those pulses so that we can deliver current at the same rates at which chemistry is happening, right? Because what you want to do is you want to map current with chemistry. And with the chemistry that you want, not with the one that you don't want. And you cannot control because everything will happen, right? So knowing what is the right time scales, going back to the lab, ran a bunch of experiments, changed the time in which the electrodes were active, the current was being sent, and you see what you expect. If there is more time in which you're sending current, you get more stop out. So things go on. You rest for a longer period of time, you get less stop out. So that's sort of expected. What was unexpected is that there is some period there's some particular pulses that allow you to produce more chemicals than if you were just feeding electricity constantly, never stopping, right? And that's because we had the right concentration of reactants in that interface to make the dimer that we wanted and avoid producing the byproduct that I didn't want. So that allowed me to move my reactants directly to products in a way that was much more efficient. And this led to like a better selectivity between those two molecules. And that was exciting because the same reactor, the same chemistry that's happening inside, I just operate it differently, I get 20% more. So, like if I'm a boss of a chemical plant, that's amazing. I don't have to build a new plant, I just change the way that I deliver electrons. But we knew one thing, which is that we really didn't know much, and we didn't know if those processes were optimized. So at that point, I had no idea of machine learning. I just had just heard that it was really cool. So I sent a video with funky music to my student about artificial neural networks, and like, can we build models that can like mimic this? And like, we build regressions, and this is a somewhat simple optimization problem. You have two variables in one optimization, one objective function, which is production rate of what you want. Here's the data that I showed you before, but just plotted differently. So you have active times, restive times, and in colors you have production rates. Here's your dot that produce 20% more limonitrile than constant current. So we build a regression model that, it's a surrogate model that follows a trend and gave us some predictions of what could happen under other pulses. And we went to a lab and told them, well, let's give it a try. And she did, and we went from 20 to 30. And we did that by further reducing the production rate of the byproduct. So now we have a process that is 30%, produces 30% more stuff of what I want to produce. Same reactor, same chemistry. The only thing that has changed is the way that I dose the potential. So that was very exciting. And my students were so excited that they decided to start a company called Synthetics, which Daniela still leads as a CEO. You might have heard about this company. Initially, the idea was to commercialize those developments from that pulse electronic system. But after 2 or 3 pivots, now the company just sells software for machine learning optimization for chemists. Because is there any chemists in the room? Okay, so chemists don't usually use computers. I mean, no offense to them, but like we're like what Synthetics is trying to do is like trying to provide them with solutions that can help them implement these type of techniques without necessarily having to like know how to program machine learning optimization algorithms, right? Like we do that in our group. That's great. Yeah, full disclosure, I do have a financial interest in this company. But it's my student that is really running it. I'm no longer necessarily involved in the company. So this was exciting. It's great. They created a company, created jobs. Like now they have raised like more than $2 million. And Daniela is a superstar. Like she's on Disney Plus on this documentary On the Room, which is about her journey of entrepreneurship. But what do we do? Miriam. So Miriam Patey was the previous CEO of the company, which is no longer with the company. She was an undergrad student here at Canton. She worked in our group too. Yeah, she was in chemical engineering. She was the valedictorian in 2018, I want to say. Okay. Yeah. Okay. Yeah. Actually, Miriam, as an undergrad, was the person who came to my office and asked me, like, I think we should start a company based in this. And I'm like, I think we're too early. And I think we were both right. But I'm glad that it happened, right? Like they went on to all of these entrepreneurship challenges. They won the NYU venture tech competition, and that sort of got them going, right? Like now they have capital from a variety of sources, including grants, friends, family, investors, VCs, like I don't know, like wherever they can find funding, they get it. But in our lab, like we had sort of this realization, right? Like this is one reaction. Of course, scratching the surface, we sort of understand a little bit more about what's happening, how to control it. There's a whole range of reactions. So then we work a little bit on the next step towards nylon, which is making this molecule. I'm not even going to mention the name. It's a very long name. We started to think also about ethylene and propylene, and not only from oil, but from other waste resources to bring circularity to the production of these chemicals. And I'll just show you like some brief results. And this is the project that we just got started maybe like less than a year ago, where we look at using food waste as a resource to produce plastics. And the idea here is that you can take biomass waste like food waste, you can put it into a reactor, which are called hydrothermal liquefaction, which is a fancy way of saying we add water and we add temperature and things break. And you produce biogas, which you can use for whatever you want. Rather than use it because then you generate CO2 but I guess you can use it. Hydrochar, which can help remediate soils. And then you produce a lot of wastes with every single chemical process. And that waste actually has these molecules inside, which are called carboxylic acids. And those carboxylic acids, you can transform into ethylene and propylene, which you can use to make polyethylene and polypropylene, which I'm sure you have heard. These are the biggest plastics in the world. And then on top, you get hydrogen side, which is kind of like a nice added product. And I won't walk you through some of the details of this complex chemistry into it. There's many things that can happen. But Andrea, over the past year, has figured out a way to run these reactions with more than 50% selectivity towards what we want instead of everything else at really high production rates. So we're excited to move forward this project as well, because it will lead to a path to produce bio-derived ethylene, which will allow us to not necessarily have to extract oil to make ethylene. Which is great. So those are other molecules. There's a whole bunch where we think that electrochemistry can play a role, and not only us, but people that we work with outside the university. But this is really large, right? Like I told you something that has taken us, I don't know, 5-6 years to like start to get to understand. And we only have 30 years to decarbonize this industry. So we need to move faster. So one way to move faster is by looking into autonomous and high throughput experimentation routes to this type of workflows, to this type of chemistry. And you can do this by using parallelized electrochemical reactors. So now we have this little cell that we put together with robots that can prepare different chemical solutions, and we can run 24 reactions at a time instead of one at a time. And since the volumes are much smaller, they can take, what is it, like 1 to 5 minutes, like or so, per experiment. And you get 24 all at once. Then the robot can prepare like your samples so that your analytical tools, which are these like fancy things that you see here. This is NMR, so that's stands for nuclear magnetic resonance. Basically, it tells you which molecules you have and how much of them you have, by giving you a spectra that looks like this. That's like complex peaks, and they're difficult to understand. What we have been doing there is using supervised learning. Like now that we actually know a little more machine learning, to actually extract quantitative information about how to use this spectra to know what my reactor made in a way that is fast. And then tell a machine learning algorithm, which I'll tell you a little bit about, called CHIDO, for chemically informed data-driven optimization, which in Mexican means cool, if you didn't know. So that CHIDO can tell the reactor what to do next. And the idea is to have all this integrated, and then have these guys like be thinking about what is the next chemistry we're gonna try, and what are we actually serving in this reaction. So let me just tell you about CHIDO, because I know that there's a lot of machine learning work happening in cost, and like this is just the beginning of something, right? And the premise behind CHIDO is that we spent 100 years learning about chemistry and learning about chemical engineering. We shouldn't be throwing that away, right? Like there's like all these like beautiful equations that we can use to model chemical reactors. This sort of work, but not 100%, right? Like, because otherwise we wouldn't have a lab running experiments. I'll just be running experiments in my computer. So they're not fully predicted. But they can give us an idea of what's happening. They can point us in the right direction and whatnot. And we shouldn't throw that away and just say, but I just not going to data, then have data drive everything. I could do that, but getting data in chemistry is expensive. It's a big challenge. So while there is a big problem with big data in many fields, the problem in our field is a problem of small data. How do we extract maximum information from the amount of data that we have? And one idea was like, why don't I combine this machine learning optimization, which is really based on optimization in our case, with our physical models in a way that we leverage the good things from both worlds. Like these models, I know they can work sometimes, like sometimes they work better than others. Data is always right. If a reaction, like the molecule knows what is happening, like even though I don't know what will happen. And we started to think about how to blend these two things together. And we did this work actually in collaboration with Chris Musco in computer science here, where we thought about first, well, take the physical data to give you a sense of like what is the balance of your parameters, like where do you want to run your experiments at? That will tell you that first batch experiment that you then go ahead and run, you collect some data. I'm just using the previous example just to give you a sense of how this works. Then you can go back to the physical model and predict what will happen in other points, just to feel the space a little bit better, right? And get a sense of what the space would look like. So you can build perhaps a better surrogate model for the next step of your basic optimization. And then that surrogate model, via an acquisition function, will sort of guide you towards areas that you predict to have high performance. I'm going to use the word, the E word. We run that experiment. We add the data to my basic optimization algorithm. We erase modeling data. And then as I progress, I have more data-driven models than at the beginning, right? And if I have a really good physical model, I'll converge to the optimal really fast. If I have a really bad physical model, at the end, it's just going to be a data-driven optimization problem, right? And long story short, when we run these with like some toy functions and also with some electrochemical models, you can actually converge faster than just regular basic optimization. But the reality of it is that if your models is not good, data is king. Yes.
Do you mind if I ask something?
Go for it.
So I'm sure it's a matter of space, but you're only showing the bulk emissions. There are no boundary conditions.
Yeah.
Boundary, my experience is that the boundary is where the biggest mess, or it's not the case.
For the physical model? Yeah, I mean, so I show those equations as an example. So yes, I mean, like for those equations, the boundary is really where the biggest problem is. But like in terms of like uncertainty and like when the model don't work, it really has to do with the reactivity. It's like I don't know like what reaction will happen in my catalyst at a given current density. So for that you need to develop molecular models, and those are terrible. They're not predictive at all. So the transfer model actually is quite good.
But on the surface, it's a mess.
On the surface, it's a mess.
So what I'm saying is that when you think of the algorithm, if the algorithm accounting for change in potentially boundary conditions, like if your boundary condition, that's how do you balance between optimizing with the bulk versus optimizing with the
well, like what I'm optimizing here is that for my purposes, what I want to optimize is either a production rate of something, which is not necessarily a boundary property, it's a reactor property, right? I want to optimize that. I want to optimize selectivity, and I want to optimize energy efficiency. And actually, I want to show this here. What you really want is a balance, and like we have been doing some Pareto prompt analysis on like what is this optimal trade-offs between these operations, because you give this to a plant and basically tell them it's like, well, this is like the best that you can do. You pick. Do you care about energy more than you care about production rate, or do you care about selectivity more than you care about energy? Like, and those equations will change depending on the price of energy. And but this is our general framework. Yes.
Just perhaps to move on to the question. How do you solve the question of availability? Because the question of surface,
yes,
in my understanding, is more and more important at a small scale. And to build the ground truths, you need some data. And my understanding is that, I may be wrong, there is here a question of how can you use models and the data at a small pilot scale, to the big industrial scale. Is this a problem?
Well, I mean, I think, I think I got your question, which is like, there's some disparity on like what happens in our understanding at the small scale and the big scale, right? My premise, the way that we have been moving in our lab, is that I don't know how to model the molecular process that happens where the reaction takes place, which is a big part of the reactor for sure. So for that, rather than for me build a model so that I can, like run a function and like get an answer, I just run a function in the lab, and I get the answer in the lab. So we're thinking about experiments, same way that we think about functional evaluations, and trying to integrate with things that maybe we can model better. So our first initial attempt to bring together physical models for chemical processes and data-driven optimization is what I'm showing you here. As I show you, it's not that different than basic optimization approaches, which, you know, I mean, at the beginning, it's like, yeah, this is really disappointing. I mean, like, this was something people wanted for this to be transformational. It might help a little bit, it doesn't hurt. So if you know something basically about your system, include it. But I think what really points us is that there's some good opportunities there on how to best integrate. I don't know the answer to that, like we have had a few discussions on this, and like another idea is use the physical models to provide physical bounds to your survey model predictions, right? Rather than mix like physical model and data, then just use that as constraints. And that's something that we haven't tried. Like, I don't know anybody that have tried it in chemical engineering. In chemical engineering, you usually find this work on people that work purely computational. So the thinking is a little bit different. And the people that usually do experiments on use computers. So we're like, I don't know, like I'm asking a lot from these guys to do both. And it's great to be in places like this because you can then collaborate and create knowledge from other fields. Doing this with Chris, because I just didn't know what I was doing. I know a little bit more about what I'm doing now, but still a lot to learn. But yeah, I mean, as I said, like, this was not completely transformational, but it didn't hurt, right? Like, and the reality of it is that it takes time to build good physical models that in most cases you probably just want to rely on. And we're basically doing that. Like we're basically sort of regressing back to using pure data-driven optimization in our approaches. So this gives you a sense of what we have been doing in terms of manufacturing. Yeah, 5 minutes is perfect. I just wanted to like give you like a few vignettes of things that we're doing to the other big unsolved problems, technological problems in climate change, which is long-duration energy storage. This was an idea that we had a few years ago, where we were thinking of using decoupled electrolysis to solve the problem of long-duration energy storage. And the idea here is that in electrolysis, you have an electrochemical cell that splits water into hydrogen and oxygen. Instead of having one electrochemical cell that produces hydrogen and oxygen, why don't I have an electrochemical cell that produces hydrogen, an electrochemical cell that produces oxygen, and I couple them with some chemicals that can cycle in between them. And what this allows me to do is that I can produce hydrogen during some time of the day. I can produce oxygen during another time of the day. And if I pick the right molecule here, this cell will consume electricity while this cell will produce electricity. So this will allow you to, let's say in the middle of the day, in the summer in Germany, where you have excess electricity, solar electricity production, and prices go to negative, you produce a lot of hydrogen. And they pay you to produce it because you're taking energy out of the grid. And then at night, when there's no sun, you close the cycle and produce oxygen and put electricity back into the grid. And at the same time, you're storing a lot of hydrogen, which you can then use in a fuel cell to produce more electricity if you ever want it. And the nice thing about hydrogen and any chemical fuel is that we know how to store it for a long time. We can put it in a tank, we close it, and we come back 20 years later, it's there. Which is different than batteries, right? Like if you turn off your battery today and you come back next week, it's like half charge. So you cannot store across systems with batteries, but you can store across systems with fuels, like hydrogen. So we patented this and built the cell, we tested it. We worked with Yuri Forkin, who was here at NYU before, to try to understand how would you couple this with a grid, right? With a real, price fluctuations and the constraint that you need to produce 1 molecule of oxygen for every 2 molecules of hydrogen. Like there's a physical constraint, like you cannot get around that. And by doing that, and sort of doing some techno-economic analysis, we realized that our system, as we build it, is more expensive than a regular electrolyzer. It basically comes down of not being able to operate at high reaction rates and the fact that capital is expensive. And it points us toward direction to improve. And we have been working a little bit on moving in that direction. The other question was aviation fuels, and I won't tell you much about this, but I'll just tell you that we had a small collaboration that actually Ricardo had been helping with her company trying to bring circularity to aviation fuels, where we can transform CO2 by reacting it with hydrogens, that's what I showed you before, into aviation fuels in a way that if we capture CO2 from air, then the net carbon footprint will be zero. And this is a company that we're helping by providing access in the 8th floor of State Manufacturing Order for them to do their R&D, and they have pilot plants here in Brooklyn. So it's my understanding is the only chemical manufacturing company in the city, which is exciting, and hope to get one more. So with that, I hope I gave you some brief overview on some of the things that we're doing and we need to do for our planet and our climate. And I wanted to sort of talk about cities, like since I'm in COT, I haven't talked about cities at all, and I just briefly discussed at the very beginning. What do we do about cities? I mean, like cities are actually great in terms of emissions because we have people really densely close together, like travel distances are small. We still need to do a lot to decarbonize cities because, you know, although this is the carbon footprint of a household in the city, we really need to bring this down to zero, right? And the city is committed to do that by 2050, and there's big engineering challenges to do that. I think we do have the technologies to do that, but the transition is not easy, and I think that's what we should be working on. We need to be really figuring out how to really enable that transition. Thank you. Thanks to all the people that do this work. Thanks to all the people that give us money to do this work, and thanks to you for being here.
Thank you, Dr. Modestino. We have roughly 11 minutes for questions from the audience. So feel free to raise your hand, and we will do by order if we have a lot. I can start with it. Okay, I have a bunch, but I will start with one and see how we do. So in the ANN BNN experiment, was that simulation results or was it actual?
Pretty much all the results that I showed you, except the Chido, were experimental results.
So those were experimental results. And on that experiment, so what was the control? Because there was machine learning component, right? So what was the part that you were controlling using machine learning, and what was the output that you were getting?
So what I wanted to find was what are the optimal pulse times for this process to maximize production rate of electrochemical, which is the molecule that we want, right?
Okay. Okay. My second. Okay, so Elizabeth.
Oh yeah. I have a question about scale, actually following up on yours, but in the other direction.
Okay.
So thinking about the math that you just showed and how you can evaluate carbon footprint on a household scale. Are you guys thinking about?
That is from the New York Times.
Yeah, totally. I thought you were coming with the New York Times. No, just thinking about things at a household scale.
Yes.
I mean, are you guys thinking in that direction at all? Because I think that oftentimes in the narrative around climate change, oftentimes the onus is put on the individual to change their own behavioral habits.
Yeah.
You know, so like the plastic problem is because we don't put plastic in the recycling bin, for example.
I don't agree with that narrative.
Which I think is erroneous.
Yeah.
But for example, you know, there's a lot of support from the state to put solar panels on your roof if you're a homeowner, for example. And
well, I mean, like that I think is a little bit different. Yeah, like the question about like, you know, should consumers not be using plastic? It's like, well, yes, if you can, we should all try to do our best, right? Like, you know, we're all in this together, we live in the same planet, like so. And as I said at the beginning, like it's not like we're gonna kill the planet, it's gonna kill us. And I don't want that to happen. I don't think it will happen, but like we will suffer across it. But the solar panels question is a good one.
or for example, the energy storage that you just mentioned, do you imagine that on a household scale?
I don't think so. We usually benefit tremendously from efficiency of scale. Sorry for the E word again. It's just cheaper, and we value money for for one reason or another. So usually we try to do things that is cheaper. So you make the system bigger, then it'll be better. If we go back to that particular case, there are things that are modular in which the economies of scales are not necessarily that strong. Like these reactors, they scale by area rather than by volume. But the storage scales by volume. So you still benefit quite a bit by having everything co-located. Like my vision is that the future of chemical production and energy storage and energy production is still centralized. You might see a little bit less centralized than it is today, but still, I think you'll benefit from centralized. It's like, would you need to have like, you know, I don't know, like 100 square mile like chemical plant? Probably not. Like probably, you know, like a size of a building like this will probably do. But that's sort of where it'd be, I think.
I can follow up on this. So what would be, based on the results that you've had, what would be sort of a timeline in terms of how much can we store economically, and how much can we store economically in order to be able to, at what point can we do that in order to be able to follow some of the pathways that you mentioned in the beginning when we were decarbonizing?
I don't think I fully understand your question. I'm gonna try to answer it anyways.
Okay, so to decarbonize, I guess in the US, we choose to electrify, right? Mostly.
Yes.
And so to do that, we will need long duration storage at some point in order to address, for example, seasonal fluctuations in energy demand.
Yeah.
And daily fluctuations, but mostly seasonal, the long duration is the example. So right now, from what I understand, it's really expensive to just put these batteries everywhere. So how, if you were to give sort of an estimate at what point does it get economical?
What would be economical?
Yeah,
I think it's economical today, so we're not factoring the externalities. It's a matter of also factoring the externalities. Like, will we ever be able to be more economical than generating energy from fossil fuels and emitting without factoring the externalities? I think probably. But it will really help if we factor externalities. If we factor externalities, it's still like it's completely economical. Just to give you a sense of this, I flew to Europe in December. You emit roughly like a ton of CO2. Companies that are like working on capturing CO2, I don't think anybody can capture a ton of CO2 for less than $1,000. So that's what you need to add on top of your ticket, because we should all be picking up our trash. But unless somebody forces us to pick up our trash, we'll just keep putting trash out, right? Like, why don't I go around throwing trash in the street? Because it's illegal, they'll fine it, right? But for some reason, it's okay.
makes sense. Thank you.
So I had a question about, the production of ethylene and polypropylene from the biomass. So you're having to heat that up to produce the gas and then the solid product. What is the kind of economy of the emissions from the heating versus the gas being produced, or would it be electric heating?
Yeah, that's an excellent question. Let me go back to that diagram so that we can talk about thermodynamics. Okay, thermodynamics. There is more energy here than here. So I think if you think about it thermodynamically, you could run this process without external energy by extracting the energy from the hydrogen produced, for example, or whatnot. Does heat equal CO2? The answer is no. You can electrify heating, as I said at the beginning, and we should. And we should use heat wherever it makes sense to use heat. It just needs to be decarbonized, right? And I think the way to decarbonize heat, for most cases, is by electrifying. There'll be cases in which it'll be hard to get electrical heat at the temperatures that are needed. In that case, I don't think I would justify burning fossil fuels because you can always burn hydrogen, and that would make more sense to me. If you burn fossil fuels, you can still capture it. I don't love that idea because I don't think it's sustainable or scalable. To the scale that we need. I mean, it's scalable, but like not to the scale that we need at a planetary level. So that's why when we think about climate change solutions, we start with the priority of avoiding, right? Like if you can avoid, you should avoid. The case in which you cannot avoid, so you capture. If you cannot capture, you can disperse it in a plane, it comes from air. Or let the plants capture air, right? Like and close the valve, close the circle, right?
I have a question about this figure also. So that's a fermentation process, right? It's producing the biogas from your food.
There's no loss. This is just heat. Yeah. Yeah. I mean, like, I would love to know about more books, but I know that we're hardcore Italian now because I don't know anything about books.
Yeah. Cool. Yeah, because you could think of like trying to select or inoculate for specific populations that would have like secondary metabolites of interest.
Yeah, I mean, like if you do this at low temperature with box and you make a lot of peroxide acid, you make plastics. And I think you can do this, right? You make vinegar all the time. So. Which vinegar wouldn't, but right? Like you need to make propionic acid.
Okay. So let's give another round of applause to our speaker today. And we will convene next week in the same room, 12 p.m. this time, and we have Dr. Joxi Pan as our speaker. Enjoy the weekend.
Thank you.